Hello, I'm Nikhilesh Narkade, student of HPSC, MS in Data Science. This recording is for final project of HPSC. This is my final project where I have implemented HPSC concept for music genre classification for music recommendation system. I'm Nikhilesh Narkade. The problem statement of this project is that the music genres I build a deep learning architecture to classify music into top 10 genres. Now, the audio data are time series data. If we go with the traditional time series architecture like RNN, the LSTM model turn out to be very bulky and faces problem like vanishing gradient. But if you see what does audio data is nothing but it's a set of frequencies. So we can convert audio data into image format using a spectrogram with a library like Librosa. It's representing of the spectrum of frequency in sound recording as they vary over time. As you can see, this is an audio data.wav. This is the spectrogram creator which I have written in Python using Librosa library. It is getting converted into an image. It's as you can see in the image, there are three different color. One is the dark color, followed by orange and blue, uh, orange and yellow. The dark color shows the low intensity frequency, whereas orange and yellow area showcase the high intensity frequency. This is the another link you can see more about the spectrum. Okay, coming to the architecture, as I have to classify the audio data into different genre. This is the architecture I have used, where audio data is the input, which is converted into a spectrogram, given to a spectrogram creator. Now, this spectrogram creator will change the audio database into a spectrogram image database. Once the image database is generated, the 80-20 split, we split the data 80% for training and 20% for test. After that, we use image data generator, which is ready-made class available in TensorFlow to load the data to train the deep learning architecture, and followed from here as we have converted the audio data into image data, we can apply a CNN followed by a fully connected layer having an output layer of 10 to classify 10 things. In this architecture, I have implemented HPLC at the time of spectrogram image generation as well as multi-threading at the time of training a deep learning model. Let's call this process as pre-processing data. I have used Librosa and ipyparallel for parallelization. For deep learning, I have used multi-threading, which is available in TensorFlow. For pre-processing, for example, let's pick one genre. Let's say rock. In a database, I have 100 songs for 30 seconds each. Duration of each song is 30 seconds each. So once I can parallelize it using ipyparallel. Let's say if I declare 4 worker, then each worker will have 24 songs to work on. Whereas in at the time of deep learning training, I have used OpenMP, interoperation parallelism, and intraoperation parallelism. Okay, coming to IP parallel for distribution computing. What is IP parallel? Python library that ensures parallel tasks execute using multiple worker idle for distributed computing. It's based on MPI. Key concept: the controller, which is the one who is like a master, distributes the task and maintains the status, whereas engine executed the task independently. For example, for the given each engine would be doing the same task. Each engine would have a function of a create a spectrogram, which will take input as audio data and convert into a spectrogram image file. The example is the same, the parallel processing of audio file into spectrogram image to reduce the computational time. Improvise efficiency, reduce a scale to multiple core system, and seamlessly integrate with Python. At the time of deep learning architecture training, the OpenMP optimization means it makes sure that the CPU-based computation are distributed across multiple core. For example, in this, we are using a convolution layer and a metric operation in a fully connected are parallelized. The OpenMP ensures that the operations like matrix multiplication for the filter in the convolution layer and the weight update in the dense layer are executed across multiple CPU core. Now, coming to interoperation parallelism. And what does interoperation parallelism mean? Let's say each core has a two thread, and it if a task given to them in such a way that in task A and task B are independent of each other, the interoperation what will it do? It will give a task A to the thread A1, whereas task B to thread C. Manages a parallel execution across the different operation in computational graph. For example, if a two convolution layer are computed independently during a forward propagation, the TensorFlow can process them coherently. Pooling layer and a dropout calculation can be executed in parallel with certain independent layer. Interoperation means now as we have distributed a task A to thread 1 and task B to thread B, the intra-operation means let's consider the thread 1. Within that task A, it will try to find is there any possible to have a parallelism within a single operation. So if, for example, for each convolution operation, a matrix multiplication between input data and convolution filter is broken into a smaller task. The pooling and activation computation like ReLU for large feature map are divided among the threads. The benefit of using multiple threading in the TensorFlow is improve the efficiency and reduce the execution times, scalable across multiple core, and better utilization of computational resources. These are the findings I got after implementing for pre-processing. I have used ipyparallel. After using ipyparallel, these are the three graphs: a number of core versus execution time, number of core versus speed up, number of core versus efficiency. As you can see at the leftmost, the execution time drops exponentially, as well as the speed up grows linearly. And if you see at the efficiency for a number of core 2, we get a highest efficiency. And one of the another information we can extract is as the number of core increases, the efficiency drops. Even though we are getting more speed up with more core, the efficiency is dropping. It might come at some cost. These are the results at the time where I have used multiple threadings. As you can see, same execution time followed by speed up and efficiency. The execution time dropped exponentially. The speed up, there was a certain increase. Like for example, if you use 4 multiple threading, there was a sudden increase in speed up. And as you can see, if you are in terms of efficiency, the number of core, if we have a 4 number of multiple threading, we get a highest efficiency. After finding the conclusion is that pre-processing data, that is nothing but if you have to convert audio data into a spectrogram, two workers are most preferable. In this context, if efficiency is given more weightage, like as you can see, for two the efficiency is highest, and there is a sudden drop in execution time. Whereas if your priority is the more to reduce the execution time, you can go for four worker. From the four worker, there is not much. If we keep on increasing the number of four, there is not much change in execution time. Whereas at the time of deep learning, in terms of both execution time as well as efficiency and speed up, as you can see, if we go for four multiple thread, there is a sudden drop till 4. There is a sudden increase in speed up at when the number of multi-thread are 4, and at the time of efficiency, we have a highest efficiency when we apply a multiple thread. The one of the key problem of deep learning are new data keeps on generating. We have to update our model. So at the time of retraining that model, we can do a setting in such a way that at the time we can have a four multi-thread worker for this architecture, so that we will get both execute better execution time. Means it will reduce the training time as well as it will be efficiently using the all resources. Now coming back to the programming part, as you can see, this is the program where this is where the data is. You can download it from this word file, as it's like 1.5 GB. After you download it, you can get to know about the structure in a readme file. The whole structure is that first the pre-processing data takes place, where this is the Jupyter notebook which takes files from the data, and it converts the data into spectrogram. This is the program where I have imported the required library like librosa ipparallel. This is the function which is converting audio data into a spectrogram. This is where all the directories is been taken care, and this is where I'm converting a spectrogram into a given uh, audio data into a spectrogram images. And this is where I'm experimenting with a number of four. Here I have experiment both. So starting with 1, and at the max it will go till 8. As you can see, the execution time for one engine was 162, then it decreases to 78, followed by 54, followed by 41, followed by 31, followed by 30. As the core increases, the execution time reduces. This is the visualization for a number of core that I discussed in the PPT for pre-processing. The same goes. The same goes for. This is a notebook where I have visualized the number of core versus execution for deep learning. For deep learning training, to declare the number of thread, the TensorFlow has a within setups where you can declare number of workers, and you have to declare the threading inter operation parallelism thread, intra operation parallelism thread. Like for example, I have to declare a single thread. Uh, I will declare it as a 111. If I have to declare 8 multiple thread, I have to just replace this value with 8. The whole notebook will be same. As you can see, this is where the epochs training takes place. For single core, the time taken by folder was 6,102, which is around 100 minutes. Whereas time taken, if I increase the 8 multiple threads, the time execution reduces to 707 seconds. Now, I have done experiment from both, from worker 1 to worker 8, and all this information about number of core, like number of threads. I have wrote a function which will take input as a number of threads as well as number of time. This is how much time it takes to train, and it will dump it into an text file called core data. So all the information is been stored as this is the result. If I if I see for single thread, it takes this much time. As the time increases, the time keeps on decreasing exponentially. The minimum time was for 8. To visualize this, I have imported this data and imported this data into this Jupyter notebook. This is the same value what we saw in the core underscore data. This is the number of threads, whereas this is how much time the model takes to train. So this is the visualization, the same discussed in our video. Okay. Coming back, this is how I achieve my problem statement, where the way first I use Librosa library to convert my audio data into program. Then I use inbuilt features of to split the data generation. To load the data, I use image data generator. Then I use TensorFlow for designing architecture and training. And output of this is a general classification. And in this, at the during of spectrogram, for pre-processing and model building, these are the two findings I have. Thank you.